Today we continue our discussion on OpAmp, operational amplifier 221. And the last week we discussed the OpAmp. What is OpAmp? We said that it gets two inputs. It's like a triangle shape device. Gets two inputs, plus minus, and the VO as output, and subtract the inputs and multiply the difference by a constant number, which we call it gain. Okay, so the plus input, we call it V sub P, and the negative input, we call it V sub N. The other names for VP and VN are non-inverting input for positive terminal and inverting input for negative terminal. And of course, we have a VO. And what is the VO? VO is equal to A times VP minus VN. Okay, so I mentioned that we have two important rules or equations in OpAmp problem. The first thing is always in order to solve op-amp problems, we should consider Vp equal to Vn. They are always the same because otherwise the op-amp will be in saturation mode. And the next thing we should consider is the current. The current entering the positive terminal is equal to the current entering the negative terminal is equal to 0. Okay, and usually in order to keep op-amp in the linear region, we need to have a feedback, the feedback from the output to the input. So that helps to keep the op-amp in a linear region. So last week we saw an inverting amplifier which can amplify the difference between two inputs, and we were able to change the gain. Of course, when we have an op-amp, when we have only a single op-amp, just an op-amp, we know that gain is A, and A is very large number, so it's not useful. We don't like it because with any value for VP and VN, the op-amp will be entered to the saturation mode immediately. So this A is not what we discussing. When we calculate VO as a function of VS, VS could be like difference voltages between VP and VN. So this value can be equal to a number, the constant number KV. So this KV is dependent to the resistors that we connected to this circuit. So we can easily manipulate this voltage gain, okay, and get the desired voltage gain that we're looking for. Then if you remember last week, I tried to change the value of two resistors and the gain changed between 10 to 5 and any other number. Any question? Okay, so here I'm going to show you the second example for op-amp. The second example for op-amp, which is, before talking about the examples, let me introduce, talking about the inverting amplifiers, and then I will talk about, because the last thing we discussed on the last class was non-inverting amplifier. So here I'm going to first tell you what is inverting amplifier, and then we start with examples. So inverting amplifiers. What does it mean, inverting and non-inverting? So when we have a input, we get an output. So we have input, we have output. If the signs of the input and output are same, we call it non-inverting amplifier. If the input is positive, we get positive output. If the input is negative, we get negative input output. We call it non-inverting amplifier. The example we saw last week, but inverting amplifiers are those amplifiers that the sign of input and output are opposite. So in inverting amplifiers, if we apply positive input, we get the negative output. Negative output multiplied by a constant, multiplied by a constant gain. Okay. If the input is negative, we get like positive. If the input is positive, we get a negative. Okay, so uh, we can say in non-inverting output is KVO, KVS. Let's assume K is a positive number. And in inverting amplifiers, VO is negative KVS. Okay, so that's it. So VO is negative KVS for inverting amplifiers, considering K is positive number, and for non-inverting VO is KVS. Okay, the last example we discussed last week was non-inverting amplifier. So the output was the same sign of the input. Here we want to see what is the inverting amplifier. So here is the inverting amplifier circuit. We have the OpAmp. OpAmp is connected to voltage source Vs, R1, VO, and this time the feedback, we always need to have a feedback. The feedback is like this, and positive terminal is connected to the ground. Okay, so by the way, before continuing to solve this one, sometimes we show amplifier negative, positive like this, sometimes positive, negative. Like there is no big deal. It's like we just flip the amplifier, flip the op amp. Okay, here the top input is VN and the bottom one is VP. Okay, we want to find the output as a function of input. Like I'm going to tell you the rules. The rule is look to the two inputs, VN and VP, and see which one is known for you, which one is like known, which one you can calculate, like find the voltage immediately. If you look to VP and VN, the VN here is connected to the output and the input. So as long as we don't have any idea about the output, we don't know what is VN. Okay, but if we look to if we look to the VP, we immediately see that the VP is connected to the ground. So we know the value of VP. Okay, so we say VP is equal to 0. Is equal to what? Is equal to, based on the rules that I mentioned, equal to VN. So this one is the main step. So this one is the first thing we need to do. Then we look for a node that connects the input and output. If we look to here, we see that here is a node that connects the output to the input. So let's write KCL for that specific node, which connects the input to the output. So we can say Vn minus Vs over R1 plus Vn minus Vo over R2 is equal to 0. We didn't consider the third branch, which is this branch, this branch. Why? Because we know that the current IN is equal to 0. So when the IN is equal to 0, of course, it's equal to 0. So even if we consider it like the value of the current is 0. So here we have our equation, Vm minus Vs over R1 plus Vm minus Vo over R2. And of course, we know that Vn is equal to 0. And as a result, we can simply say my negative VO over R2 is equal to Vs over R1. As a result, Kv, which is equal to VO over Vs, is equal to negative R2 over R1. And here we see that the gain is negative. Okay, so you see that the like kv is negative because r1 and r2 both are resistors, positive values, and the negative sign before in front of them like indicates that kv is negative. Okay, so it's the reason we call this amplifier as inverting amplifier. Any question? No questions? Okay. Okay. Now that we learned the principle of amplifier, Alex, you hear me?
Yes.
Okay, good. So we learned the principle of the amplifiers. Let's move. Oh, by the way, before moving to the examples, let me plot draw a graph for you. Let's say this one is like V time, and this one is a voltage. And if Vs, for example, is this voltage, let's call this Vs. What would be VO? VO will be something like this. You know, you see the like opposite sign of input multiplied by a constant. Okay, so now it's time for solving some examples together to get like mastering amplifier problems. Okay, it's example. In the following circuit, find the voltage gain. Of course, we know that the voltage gain is VO over Vs. And here is the circuit. VO. Okay. Now we want to solve this problem and find the VO as a function of VS. What is VO? What was the first step? I said we look to the input and see which input is known for us. If you look to Vn, let me just label them Vn, Vp. If we look to Vn, we see that the Vn gets an input feedback from the output. So of course the value of Vn is not known for us at this moment. But what about Vp? Vp is connected to like two resistors and one voltage source. Can we find the value of Vp or no? The first thing, which is very important, again, I emphasize it 10 times, 200 times, no matter, is that like the current here is equal to zero. That's very important. Okay, so when the current entering to positive terminal is equal to zero, we want to find the VP. Okay, VP is the voltage across which resistor. The VP, of course, is the voltage across R2 because we see that VP is connected to the light terminal of R2, and we need to find the voltage across R2. Can we find it or no? Let's see. Because the current entering to this branch is zero, we can just ignore this branch because there is no current moving through it. And in order to find the voltage across R2, the simplest way is voltage division, because we know that like there is only one loop here and there is a voltage division. You might ask me, what about the other loop? I would say because there is no current moving through this branch, we can just simply ignore that branch and consider it a single branch and single loop and find the voltage using voltage division. So Vn V over R2, which is equal to Vp, is equal to R2 over R1 plus R2 times Vs. Okay, so this is the value of Vp. So we know the value of Vp because R1 and R2 are known, are given, and Vs, of course, is the input. We know the value of input, and we simply found the Vp. And we should say it's equal to which value is equal to Vn. Okay, it's equal to Vn. Very important. Don't forget to write this one. So Vn is equal. Now let's find the node. Let's find the node that connects input to the output. Input side. When I say input, I don't mean exactly the input. The left side to the right side. Which node here connects like the input side of the input of the amplifier, the inputs of the op-amp to the output of the op-amp? If we look, we see that this node here is connected input, which is Vn, to the output, which is Vo, to like some resistors. Okay, so this node is very important for us, and we need to write KCL for this node. Okay, so we write the node equation for that specific node. So node equation again, because the current entering to here is zero, In is zero, so we don't need to like write any we don't need to consider any current, and the only thing remains is V. Oh, by the way, what is the voltage of what should do we label this node? This label has a voltage same as Vn because it's connected to like Vn with no resistor. So we can call it Vn, okay? Because Vn is like the same as this node. They'll just wire it together. So we can say Vn Vn minus 0, which I don't write it, Vn over R4 plus Vn minus, what is the voltage on top of R3? Of course, it is VO. Vn minus VO over R3 is equal to 0. Okay? So this one is any question? Let me say it one more time. The first thing I said that we should consider the node which connects the inputs of op-amp to the output. So it is here. We got that point. I just put a red circle around that node. What is the voltage of this node? Of course, the voltage of this node is same as Vn, so we call it Vn. And by the way, the other side of R3 is the same as voltage of VO. And when we write the KCL for this node, we can say Vn minus 0 over R2 is equal to Vn minus VO over R3. Okay, it's the way we write the like node equations. Okay, so we reach to this point, and simply we have the values of Vn and VO. Let me just see what we can do. We can say, let's factor out Vn times 1 over R4 plus 1 over R3 is equal to VO times 1 over R3. Okay, so this one is uh, okay, that's fine. Okay, and then we can say VO is equal to R3 plus R4 over R4 times Vn. Okay, so VO is equal to, just I multiplied both sides of the equation by Rn and R3, and so it gives this result. VO is equal to R3 plus R4 over R4 Vn, and instead of Vn, we bring the Vn from here to here. We just substitute it. Okay, so we bring the Vn from our previous equation to this equation, we substitute it, and we will have VO is equal to R3 plus R4 times over R4 times, instead of Vn, we say R2 over R1 plus R2 times Vs. So this one is the relationship between the output and input, and of course KV, which is VO over Vs, is equal to R2 over R1 plus R2 times R3 plus R4 over R4. So this one is like the characteristic of this table. Is it characteristic of this amplifier? Is it like a inverting amplifier or non-inverting? Who knows? Just send me your answer by the chat box. Why it doesn't allow me to type? Okay, it doesn't allow me to. Okay, that's fine. So I ask you a question: is it inverting amplifier or non-inverting? Any answer? One answer, which is correct. Two, three. Let me. I think I receiving answer. Very good. Yeah, I got some answers for several answers that all of them are correct. Very good. It's non-inverting. Very good. Correct. Because resistors have positive values, and of course kV is positive, and so it is considered non-inverting amplifier. Good. So let's move to the next example and see what we have. Oh, before next example, let me introduce a new circuit built by amplifier, and it's called voltage follower. Voltage follower. Instead of voltage follower, it has a better name. It has a better name. We call it buffer. What is buffer? The like input is same as the output. We have buffer in digital logic circuits, in electronic circuits, in all circuits we have buffer. And what does the buffer do? Like I already explained it in the class, I believe one time. The buffer like insulates the input from the output. It insulates two parts of the circuit from each other. They both have the same values, but if something happened to like one side, it doesn't affect the other side. Okay, so like your cell phone, if you connect your cell phone instead of 5 volt voltage of your like charger, if you connect it to 110 volt, your phone will be blow up, but not the entire phone, just in the like power jack. When you connect the power like a cable, there is a buffer inside it. When the like voltage goes up, the buffer will be blow up, but it doesn't damage the like other circuits in the cell phone. So it insulates the input, the like left side and the right side of a circuit. Okay, so it's very useful device. So we need to use buffer to secure and increase the reliability of our circuits. So what is the buffer circuit? It's here. Let me show you a circuit for buffer. We have op-amp plus minus. Oh, by the way, I had a question I forgot to ask you. In the previous example, in the last example, it's very interesting. If you look to the answer depends to R1, R2, R3, and R4. But if we go up and look to the circuit, we will have, in addition of R1, R2, and R4, we have another resistor called RL, which I forgot to label it. So RL. So this resistor doesn't have any contribution to determine the output. So no matter what is the value of RL, the VO is independent from RL. Okay, so RL can be like zero, can be infinity, can be like 10 ohm, 100 ohm. If you look to the solution, we see that the load resistor does not affect the circuit. Okay, and it's very good because the characteristic of the circuit doesn't change by changing the load. Okay, now here we have a buffer circuit. We have VS, we have RS, we have VO, and here is the feedback, VP, VN, and we want to find VO as a function of VN, VS. So how we can solve the circuit is easy. Let's look to VP and VN. Which one is known for us? Of course, VN is like uh, connected to the VO, which at this moment we have no idea what's the value. But if we look to VP, because the current moving through this resistor is zero, the VP is like here, the same as for other side of the resistor, and we can simply say that VP is equal to VS. Is equal to what? Again, the same thing, is equal to VN. That's it. And now let's look to like a node that connects the input to output. If we look to the node, it's here, but to be honest, mm, there is no resistor here. Okay, RL is like not uh, contributing like our solution. So if we look to this node, what's the voltage of this node? It's VO, and at the same time, this voltage is equal to VN. So look, you see, it's equal to VO is equal to VN because like it's connected by a wire. So the voltage of that node is equal to VN is equal to VO. So VO is equal to VN. So if we put all this together, we see that VS is equal to VO. What is K? KV, of course, is VO over VS, which is equal to 1. Okay, so this one is like a buffer circuit. The voltage on both sides are set. So if something happen here, like we apply very high voltage here, and we blow up entire circuit, let's say 1000 volts on the left side, it's nothing gonna happen to the right side of the circuit. We like insulate left and right side of the circuit. So we usually use it in like interfaces to isolate the source from the load. So we isolating the source from the load. Okay, any of those like get damaged, it's not gonna affect the other part. Any question? Okay, so example, find VO when A. R2 is equal to 100 kilo ohm and RB, R2 is equal to 350 kilo ohms. Okay, and here is the circuit. VS is equal to 1 volt. R1 is equal to 10 kilo ohm minus plus is connected to the ground. Here we have VO, and here we have R2. Okay, so, and by the way, VCC plus minus, do you remember VCC? VCC is like external voltage source that we connect to op amp. So it's equal to 15 volts. Okay, so I give you 10 minutes to solve part A. Solve part A and send me the answers in the chat box, okay? So find part A. R2 is equal to 100K and send me the answer. I give you 10 minutes. Okay. The answer for this question, part A. Part A. Alex, you hear me? Just confirm it.
Yeah.
Okay, good. Thank you. Just I want to make sure that my headphone is working. So, part A is that R2 is equal to 10 kilo ohm. We don't like care about the values. The first thing we need to do is just solving this circuit like other op amps circuits that we know. We VP and VN are here. Of course, VP is known. We know that the value of VP is equal to 0 is equal to Vn. Okay, so Vp is equal to Vn is equal to 0. And now we write KCL for the node which connects the input to the output, which is here. And the voltage of that node, of course, is Vn. So we say Vn minus Vs over 10 plus Vn minus Vo over R2 is equal to 0. Vn, of course, is 0. As a result, Vo is equal to negative R2 over 10 Vs. Okay, so part A, R2 is equal to 10 kilo ohm. It was it 10? No, 100. 100 kilo ohms. So as a result, Vo negative 100 over 10 Vs, and as a result, Vo is negative 10 Vs. Vo is negative 10 Vs. Okay, now I just give you 1 minute to solve part B, because part B, like, we have the equation, and the only thing we need to do is like putting a value. Find part B and tell me what is the VO for part B. The equation is same. The only thing we need to do is substitute part A. I need to have at least 10 answers for part B, okay? So far I got 4, 5, 6 answers. Continue. For all of you, just send me an answer. It's simple. It's like algebra. Just replace the values and find the answer. Okay, so I got one, two, okay, 1, 2, 3, 4. Oh, I'm using more. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 answers. And from these 11 answers, good. From these 11 answers, only 2 of them are correct from 11 answers. For those of you got negative 35, which is like 9 or 10 of you, don't you want to just reconsider your answer? Look to the circuit. What did I do? I put like, I circled something. Do you see? So don't you want to consider your answer? Do you remember something from the last week? Very good. I see that one of you fixed your answer. The last week I said that we cannot go beyond plus minus VCC. The maximum minimum the voltage and the output is limited to the external voltage source. Very good. I'm seeing that you're correcting your answers. It's very good. It's very answer. I just saw two of you fixed it. So the rest of you, please try to send me the correct. By the way, it's okay. I got four answers. If one of you sending me like positive number, it's negative number. It's not positive. The value is correct, but look to this negative side. For one of you that sent me the positive value, it's not positive. It's negative. Okay, now I see that all of you fixing your answer. The answer, yes, of course, based on this equation, as you calculated and I ask you to do is negative 35. That's fine. Negative 35 volts. That's okay based on this equation. But we have a limitation somewhere. What's the limitation? The limitation is here. It says that we cannot go beyond this value. So if the voltage, output voltage is assumed to less than negative 15, it will be like to stay same as negative 15. If you don't get it, go back to the last week note. You see the characteristic graph for the op amp. In the like saturation mode, it was not linear anymore. It was like the constant output. Okay, if we go beyond minus plus 15 volt, so if this 15 was plus minus 25, so the answer would be negative 25. If this 15 was plus minus 50, in that case, the answer was negative 35 because still we are in the range. Okay, is it clear? Very good. So I see that you got the point. So VO is equal to negative 15 volts because op amp is saturated. So VO is equal to negative VCC. Why negative VCC, not positive VCC? Because it's saturated from negative side. Any question? Okay, so I see that you're interested in op amps. Very good. I'm happy. So let's go ahead and do one more example, a little more complicated, more resistors, but I'm going to solve it with you. So let's see. Find VO over VS. Okay, here is the circuit. VS R1, R2, R3, OpAmp, RM, VO, V R4, negative, positive. Okay, so here is a circuit, Vp minus Vn. The first thing you should notice here is what which input has like a known voltage. Of course, it's VP. VP is equal to 0. It's equal to Vn. The next thing, if you remember, I said we should find the node which connects the input to the output. So here is the node. We want to write KCL for this node. Okay, before writing the KCL, we should just consider all other conditions. If we look to R4, is Vn and Vo, that's fine. We can write the correct. But what about the voltage here? What is the voltage here? So if we want to write the KCL for the node, we should say Vn minus which value? What is this value? Is it Vs? Of course, it's not. Okay, so what should we do? The first thing we need to do is find this value. Okay, we need to find this value. How we can find this value? Let's take a look. Can we write? Can we say? Let's call it VA. Let's call it VA. Can we say that the VA has a voltage division here or no? Like what we did before. Let me go back. Let me go up. Let me go up here. Exactly here. In order to find the voltage at this point, VA, for example, I said that because there is no current moving through this branch, we say voltage at point A is the voltage division, so it's R2 over R1 plus R2 times Vs. Can we do the same thing in this example or no? Let's take a look. In the last example that we just saw, there was no current moving here. The current was equal to 0. Is the current moving here equal to 0 or no? Okay, can you tell me, just send me the answer by your chat box. Is the current equal to 0 or no? The current going through artery. Just few answer, 2, 3, that's fine. Is the current I moving through artery is a 0 or no? Okay, I haven't received any answer, but that's fine. Let me just tell you the answer. Of course, the current going through this branch is a 0. Okay, but if you look to artery, the current through artery can come from the current source, from the voltage source, and moves through artery, and through the feedback moves to the output. So we cannot say that the current is equal to 0. So it's not true. This current is not equal to 0. This current is equal to 0. Okay? But this current is not equal to 0. So as what's the conclusion? We cannot find the voltage of A by voltage division. We cannot, because there is a current here which we don't know the value. Okay? So how we can find VA? It's not easy. We cannot find it unless we find the VO, okay? Because the current moving through the entire circuit. So how should we solve this problem? Let me tell you. Whenever you get this kind of circuit, the best thing we can do is using Thevenin equivalent. So how? Here is the answer. Let's just from this point break the circuit to two parts and find R Thevenin and V Thevenin seen from this point to the left. Okay, let's see if it helps. So, what is R Thevenin seen from VA, from the this interface? R Thevenin. I'm not going to do out the circuit because we know the answer. If we turn off VS will be replaced with the short circuit, and R1 and R2 will be in a parallel. So our Thevenin is simply R1 in parallel with R2, which is R1 R2 over R1 plus R2. What is V-Thevenin? V-Thevenin, in order to find the V-Thevenin, if you remember from Thevenin equivalent, we said just consider the circuit from this point and find the voltage across R2.
Catch myself and I'll be like, ooh, they.
Oh, I'm sorry. Just put your microphones on mute, guys. So, we want to find V-Thevenin from this point. So the V-Thevenin, now that we want to find V-Thevenin, we can remove all all components because they are in the other side of the circuit and find the voltage across R2 as a V-Thevenin. So now we can use a voltage division to find the V-Thevenin. V-Thevenin is equal to R2 over R1 plus R2 times Vs. Okay, so we got V-Thevenin and R-Thevenin. Any question? This example is like finding this V-Thevenin and R-Thevenin is exactly like the other V-Thevenin and R-Thevenin. The only difference is that the entire this part is considered as Rn. So we just take it out and find V-Thevenin and R-Thevenin. Okay, so now that we have V-Thevenin and R-Thevenin, I will redirect the circuit in the new configuration. So we will have V-Thevenin, R-Thevenin, R3, OpAmp, RL, VO, minus plus, R4. Okay, that's it. So the only thing I did, I replaced this part with this part. Okay, so I found the Thevenin equivalence and then found. Okay, now we want to solve this circuit. Okay, now we want to solve this circuit. This Vp, it is Vn, and we have two resistors in series, so we can simply say that R equivalent is equal to R Thevenin plus R3 because they are in series, and then we can say Vp is equal to 0 is equal to Vn. Okay, and now we can write the node analysis for this node. Vn minus V-Thevenin over R equivalent plus Vn minus Vo over R4 is equal to 0. What is Vn? Vn is 0. So Vo is equal to negative R4 over R equivalent V-Thevenin. It's equal to negative R4 over R-Thevenin plus R3 times V-Thevenin. As a result, VO is equal to negative. Now we replace R Thevenin and V Thevenin from like the values that we found here. We replace R Thevenin and V Thevenin for with these values. So VO will be equal to negative R4 over what is R Thevenin is R1 plus R2 over not plus R1 times R2. R1 R2 over R1 plus R2 plus R3 times determinant, which is R2 over R1 plus R2 times Vs. Okay, so this one is the answer. And if we find VO over Vs after simplifying the circuit, the final answer will be R2 R4 over R1 R2 plus R1 R3 plus R2 R3 is the answer. So here we have the VO over Vs. Any question? So in this type of the circuit, when we see a like part of the circuit needs to be like simplified, we can use different methods, especially Thevenin equivalent to like simplify the circuit. And the same thing we did here, because without finding the Thevenin equivalent of this part of the circuit, it was not easy to solve the problem. So we had to first find the equivalent of this part and then replace it in this circuit. So we got this circuit. Now we can simply combine R Thevenin and R3, and the circuit becomes an easy circuit, and we can solve it. Any question? Okay, thank you.